So as I said, we're just approaching lunchtime. We already have heard interesting talks about AI, about cloud computing, about any other topic in software development or research. And now it's time for our very first talk at Big Tech Day 24 that is related to the exciting field of quantum computing. And therefore, I want to introduce you our speaker, Jens Eisert, renowned professor for quantum computing at the Freie Universität in Berlin. His group is concerned with research in quantum information theory, condensed matter theory, and the intersection between these fields. Jens Eisert's impressive track record includes grants from the European Research Council, as well as an European Young Investigator Award or the prestigious Google NISQ Award for work related to noisy intermediate-scale quantum processors. He is known for his rigorous work, but is guided in his work by pragmatic questions and practical applications. The upcoming talk today discusses the current state of quantum computing, which has made significant progress in the recent years. It will explore the near future expectations of quantum computers, highlighting their potential in machine learning and optimization, while also critically evaluating and tempering unrealistic expectations and providing a reality check. Dear Jens Eisert, many thanks for having you here today, and the stage is yours.
Wonderful. You're too kind. You're too kind. Thanks so very much for the invitation to the Big Tech Day, this wonderful event. I've been here before in the past, and I found this forum tremendously stimulating. It's impressive how you guys managed to keep contact with the most recent tech developments. And the technology we have in store today is one that's much talked about these days. That sounds very exciting, but at the same time somewhat elevated and mysterious, which is that of quantum computing. In fact, recent years have seen huge successes in the field, explosive developments, and at the same time, gigantic failures giving rise to what could be called manic depressive phases. So in this talk, we will take a, if you want, sobering viewpoint, and I will try to guide you through the potential and limitations of quantum computing. So, indeed, there's a lot being said about quantum computing. A pretty well-known review by McKinsey was arguing that the most plausible applications of quantum computers would be in chemicals, life sciences, finance, and mobility, and was estimating the gains of this to $2 trillion by 2035. I have to kind of count the number of zeros of this quantity. A former board member of Deutsche Bahn was claiming in Handelsblatt that quantum computers beschleunigt alle Prozesse. That sets quite a high bar, indeed. So is this so? So in the remaining time I have, I will go through this and I will tell you what is a quantum computer, what can it do, what not, and where are we. So, to start with, a quantum computer is a computer. It can compute the same things as my iPhone, your desktop computer, or the fastest supercomputers we have available today. It computes, it solves problems, it computes Boolean functions if you want. So a quantum computer is a computer doing the same things, but at the same time it operates on radically different premises, in the sense that the constituents are not transistors or so, but they are single atoms, ions, superconducting qubits that operate on the basis of a radically different physical theory, namely that of quantum mechanics. Now I thought, I'm not sure how familiar everybody is with quantum mechanics. I thought it would be a good idea to give a bit of a high-level overview of what this is about before we dive into the actual manic depressive phases in the field. So quantum mechanics, that sounds a bit scary to some, I would say. It's not. it's a physical theory. Physical theories are mathematical frameworks that help us to make predictions about things in nature. Say gravity is such a physical theory. If you take an apple, the theory of gravity says the apple will be falling down. You can try, the apple is here, you let it go, boom, it goes down, you do it again, boom, it goes down. That's predictive power, and the theory is that of gravity that was formulated by one of the most eminent scientists in history, and presumably also one of the less pleasant ones, Isaac Newton, at the end of the 17th century. Quantum mechanics is a physical theory like that. But it's the physical theory of the world on the small scale of that of single atoms, molecules, light quanta. But then, since this chair, me, you, we all are made from atoms and molecules, it's the theory of nature. It's the best theory we have available today. It was formulated quite some time ago in the mid-20s of the former century, after a long period of frustrations where the experiments didn't really fit together with the mathematical theories they had available. There was some frustration, and then there was a creative blast, and within less than 3 years, a number of protagonists, in particular these eminent gentlemen here, formulated the theory from scratch to a complete theory. There's a book by von Neumann, written in 29, published in 31, that's presumably more modern than any textbook that I would be using in classes today. How it came together is funny anyway. It was written at a time when there were no flights available to the public, there was no internet, there was not even Twitter available at the time. And still they made it in 3 years. See, Heisenberg was a bit ill at the time, and he spent a lot of time on Helgoland, this island, and was having long walks and baths, and was kind of working out matrix mechanics at the time. Came back, took the night train, met Born in the night train, and they worked out the Heisenberg uncertainty principle overnight in the train. It's like crazy how this came together in such a short time. It's not only a good physical theory, but it's the basis of basically all scientific endeavors that or technological endeavors that I'm aware of. It's the base of semiconductors, of materials, lasers. There is no way one can understand any of this without understanding quantum mechanics. Lasers are funny, they are quantum light, or using quantum light. It's kind of funny because that's based on a principle that Einstein kind of sneaked into an equation to fix a problem in an equation. 100 years later, the laser is in every machine for a supermarket cashier. So that is how long it takes to get basic science into application. Now, the point that quantum mechanics is basically in every scientific or at every technological high-tech product you can envision is sometimes called the first quantum revolution, and there's idiotically large numbers that people glue to that inside. Every technology is based on quantum mechanics. It's not only that, it's a very powerful theory. This is the theory number of a certain quantity in the theory, and also the experimental data, which are the same up to the brackets here. It has enormous predictive power. It's the best theory we have available. All good, all great. That said, it's different. It's radically different from classical mechanics that guides our everyday perception of our reality. For example, randomness. If you go into the lab, that was a joke, I'm a theorist, I never go into labs. There's the point that they shield theorists from the labs in order not to break it. So you go into somebody else goes into somebody else's lab and makes a measurement, say, of the spin, some quantity, and that spin can be up or down, 1 or 0. You do the experiment, you get 0, 1, 1, 0, 1. It's the same experiment, and you get a different outcome each time. It's like you take the apple, and sometimes it goes down, and sometimes up. It's kind of funny for apples. For atoms, this is like totally generic. Outcomes are random, and the theory is utterly silent about the specific outcome you have. It only gives probabilities. Yeah, you say, that's cool, it's random, it's fun, but randomness is not so crazy after all. We are used to randomness. Say, take the mother, father, diverse of all random events, roulette, like games of chance. I've played roulette once in my life, actually. That was in Las Vegas. When I came in, I put all the money I had onto the green 0. I got 0 and got lots of cash, and I was like, whoa, and I left. So that's how it goes. You can beat the law of large numbers, but that's not what randomness is about, right? The point is that roulette is random, and you get a different outcome each time, and you cannot predict this. But is this so? I mean, no. If you precisely knew the velocity of the ball falling in and the angular velocity of the wheel, maybe the wind in the room, you could, in principle, following the laws of classical mechanics, predict where the ball would end. And to my knowledge, people have used mobile phones in the past, filming the ball, and had supercomputers in the back to then run calculations and get a bias of the outcomes, and then rob the bank until people who are 3 times my width and twice my height come in and say, would you please leave? And that they do that if you win too much. So I was lucky. So the point is, yes, that's random, but it's kind of apparent randomness. You could have known it has an application. If you knew the perfect initial conditions, you would be able to predict the outcome. Quantum mechanics is different. Quantum mechanics is absolute. In the point, at the moment of the measurement, the particle decides what outcome it has. Yeah, it's utterly random, and I claim that there's no hidden substructure, no quantities inside, say, that would ultimately explain what's going on and would reveal the randomness, would be the cause of the randomness, this apparent randomness. And then you say, oh, what is this dude talking about? I mean, ultimately, it's like saying there are no pink invisible elephants. I say, yeah, I mean, they're invisible, so how would I know? It's a bit of a metaphysical question. No, there are no invisible pink elephants. So there are no quantities that would explain the apparent randomness you have. This goes away, and there's a very deep theorem that tells you that this cannot be, together with empirical observations that people see in the lab. That's captured in terms of Bell's inequalities. Ask me, you want to hear about this? This is a very deep insight that, together with experiments that have first been done by these gentlemen here, who also rightfully won last year's Nobel Prize for this, shows that there's absolute randomness in nature. The system decides in the moment what click it has. Uncertainty. You go, I'm not making the same joke again, you measure, say, the length of the table. Well, how do you do it? There's the table, you take the meter and put it there, and you measure it. And then, have you seen it? The table has changed. But that's not how it goes. The table has a pre-existing length, and the measurement reveals to me the pre-existing length. That's what measurement is about. That's not how it works in quantum mechanics. You measure, and the act of measurement will change the object. You change the state by measuring. Now you can measure a little bit, like learn a little bit, and you disturb a little bit, or you learn a lot and you disturb a lot, but there's no way you can learn about an unknown quantum state without altering the state in one way or the other and disturbing the state. It's a consequence of the Heisenberg uncertainty principle. Superposition is maybe the craziest of them all. The bit is the unit of classical information, 1 or 0, yes and no. And a moment of thought reveals that you can also think of probabilistic states. You flip a coin, and a 50-50 point would be like in the middle between 1 and 0. Another moment reveals that the state space of a bit is like a straight line segment, if you want. The quantum state of the simplest quantum system, the quantum bit, the qubit, looks like this. It's like a ball, where the up guy is still there, 1. The down guy is also still there, 0. But then you have things like 0.1 plus 1. It's in 0 and 1 at the same time. I said, whoa, what is this? I mean, the bottle is here or there, but there's no point in the bottle being here and there. Yes, for atoms, it's ubiquitous to be here and there at the same time. Spin up and down at the same time. That's very common. It's called the superposition principle. There's a famous thought experiment by Schrödinger. Speaking of which, I had a colleague in London. I was working in London for a while, and I worked with Terry Rudolph, like a founder of PsiQuantum, and we went in the evening to a pub, and then he said, yeah, we were talking about Schrödinger, and he was saying, my grandfather said something funny. I said, what? And then he said, when he was like in his mid-20s, already a trained theoretical physicist, his mom came to him and said, do you actually know Erwin Schrödinger? He said, what kind of question is that? He invented quantum mechanics. He's my hero. Yeah, there's one thing I haven't told you about. He's my dad. So he was very prolific in many ways. So this Schrödinger had a thought experiment who said, yeah, quantum mechanics is the theory of nature. So if you can prepare atoms in superpositions, you should also be able to prepare cats in superpositions. Say you have an atom that's either decayed or not in a radioactive fashion. If it decays, the poison would break and the cat is dead. That's a thought experiment. No cat was harmed in the making of this movie. And then if the atom is in a superposition, boom, the cat is also in a superposition. Yeah, that's kind of possible. And at some time people thought, yeah, quantum mechanics is not valid in the macroscopic world. It is. It's too valid. There's kind of too many quantum effects, and they kind of average out. If you could perfectly shield the cat, you could prepare cats in superpositions of dead and alive, if you want. In fact, that works for particles. If you send atoms through double slits, they can go through the left and the right in a superposition. That's very common. It doesn't decide it goes left and right at the same time. But you can also do this with fullerenes, like C60 molecules, complicated molecules, and you send them through, and they interfere with themselves. The same guy, Anton Zeilinger, also a friend, did this with viruses. Now, viruses have a bit of a bad press, right? In particular, recently, they're kind of, are they alive? Borderline. But you send them through, and if you shield them from the rest, you can make a virus interfere with itself. But that's kind of almost a living being. You ask the virus, how was it? Whoa, that was crazy. I went through left and right at the same time. Yeah, I mean, it's a matter of how to shield the center of mass mode from the rest, and then you can interfere viruses with themselves. So there's the superposition principle. Development of quantum computers, and I come to the manic depressive phase, if you want. I said it before, quantum computers are computers. They compute the same stuff. They have a classical input and output. The point of quantum technologies is to make use of single atoms, single quantum systems, to generate novel technologies in sensing, communication, like secret communication, simulation, and computing. And then you think, wait, that's what you said before, that quantum mechanics is needed to understand stuff. That's right. But now it's different in that the carriers of information are single atoms, single ions, superconducting qubits that you manipulate on the single quantum level to generate new technological information applications. This is the point of the quantum technologies. And again, quantum computers are computers, so there's the classical input. You prepare atoms, superconducting qubits, with a classical input. You make a measurement, and that destroys the state in a way. You may have a classical output, but the magic happens in the middle. You have strongly entangled quantum states in the middle that use superposition along the way. And before that, you have to have little entanglement to get peak distribution so that the measurement is not disturbing too much. It's not fully right, but it's also surely not wrong to say that a quantum computer kind of does many, many calculations, exponentially many, at the same time, which is the source of its strong computational power. Yeah, well, it's subtle because you do the measurement, so this peakness of the distribution is very important. Ask me about this if you want to hear a slightly more educated statement of this kind. So, quantum computers operate on a different level. Now, quantum computers are not wonder computers. They don't beschleunige alle Prozesse, whatever, no? They can solve some highly structured problems efficiently, which others can't, but for others, they're completely nonsensical. So there's very delicate problems where quantum computers can possibly help. It's not a new idea. Already in the 1980s, Feynman, Benioff, and Deutsch were meditating about the idea of using single quantum systems to do computing, motivated by deeply foundational considerations. The big splash came in the mid-90s when the mathematician Peter Shor understood that there are very practical problems that cannot be solved in polynomial time and classical computers, but they can be efficiently tackled on quantum computers. And he did so by deeply understanding what quantum computers are good at. He translated the problem through number theory into a problem of period finding, and this is what quantum computers can do well, period finding, and he found an efficient algorithm that factors the product of big primes that is not efficiently possible on classical computers. It's also the basis of the RSA encryption system that you would use on WhatsApp and your internet banking. I recently gave a talk in the Urania Berlin, and I asked people on stage. What came up was my daughter and the daughter of my brother. And I had two teams. One team had to multiply numbers, and the other team had to find the factors. It was kind of funny because my daughter had just learned to multiply and made a mistake in multiplying two big primes. And the numbers were 29 and 1,153. And within 3 minutes, the daughter of my brother found the factors. Whoa. That killed my story. It's a hard problem, meaning that the effort grows exponentially with the size, but with your small primes, you can do it. Experimental progress was harder to come by, and the first quantum byte, 8 qubits, was done by our friends in Innsbruck with trapped ion systems. Trapped ions are like pearls on a string. You have these single ions sitting there, and you can manipulate them with the laser in their quantum state, and they sit there for weeks. They give them names. There was Fritzi falling out after a couple of weeks. They were sad, Fritzi is gone. And then they put another ion in, and they become friends with the new ion for weeks. That was 2005. People worked hard on finding quantum algorithms, but it's not so easy. It's not a wonder machine. You have to use structure. There's ideas on solving linear systems of equations. What? That's classically efficiently possible, right? You know this. But you can do this if you encode right in logarithmic time on a quantum computer. Semi-definite programming is ubiquitous in engineering. People think about harmonic oscillators on a large scale. There are some beautiful quantum algorithms that solve some problems much better than classical computers, which is wonderful, but we need more of that type. Only as recently as a bit more than 5 years ago, protagonists took a lot of money in their hands and set out to actually build quantum machines to a large scale. In 2017, there was this IBM 16-qubit computer. There was the IBM 50-qubit computer a year later. There was the Bristlecone Google 128-qubit chip in 2019. And the biggest quantum computer we have available today is the over 1,000-qubit quantum computer at IBM, 1,124 qubits. Yes, it's not huge, but don't forget, the Hilbert space dimension is 2 to the power of 1,000. And they're also still noisy, but then such devices were completely in the realm of science fiction just 5 years ago. So it does create an interesting state of affairs. And you ask, wonderful, what can we do with these quantum computers? And that's a hugely exciting and also difficult question. And that led to quite some manic depressive phases in their own right. It's nice that we have these quantum algorithms, but all this narrative comes along with expectations that you can solve things, problems that are industrially interesting. The reason why I'm invited here is presumably because there's a technological promise after all. Do quantum computers have applications in combinatorial optimization, in machine learning, or so? And that's what we look at in the remaining time of the talk. I keep it even shorter so that, because on the behalf of our chairman, so that we have a bit of time, because I know I'm between you and lunch. It's a delicate position to be in. Combinatorial optimization is ubiquitous in any kind of industrial endeavor. We work together with the Deutsche Bahn, who's known for its wonderful timetables. Like also here, we are in motor world, right? We have a grant together with Porsche, who's thinking about notions of combinatorial optimization in their scheduling and routing process development when building Porsche cars. So these are interesting problems. They're ubiquitous. They're also usually NP-hard, which means that there is no polynomial time algorithm that will solve all problems in polynomial time. It doesn't mean that no instances can be solved in polytime. There's even the term NP-easy. Do you know this term? It's kind of cute. It makes reference to the fact that if you have a carb reduction from 3-sat, then you can run highly optimized 3-sat solvers to solve your technical problem on these off-the-shelf 3-sat solvers. Of course, it will not have poly runtime in worst case, but for many practical problems, you can just do it. It's NP-easy. Yeah? Good. NP-hard problems, such as, say, integer programming, which is like this. You have an integer-constrained linear program. However, this NP-hardness also means that there is no quantum algorithm that solves all instances of polynomial time. So what is even in store? So quantum computers will not be able to solve traveling salesman in polynomial time, ever. So what's in store? What is the hype about? And this is something we looked at, for example. Yeah? We found, in principle, yes. There are quantum advantages, but it's subtle. There are some instances that can be well approximated in polynomial time on a quantum computer that can probably not be well approximated on a classical computer with a super polynomial proven separation. So the hardness, easiness regions are kind of shifted. And this is what is in store. Yeah? And that's exciting. So this shows that quantum computers can offer advantages in combinatorial optimization in a subtle way. But then the depressive part is that I couldn't resist finding a Hamiltonian that would encode the problem at hand, but it's not variational. It's not of the type of having knobs and then turning the knobs and in a variational fashion solving the problem as many players like IBM, Google are running. This race for variational quantum algorithm is still open. That's the depressive part, that we have no guarantees that they would perform well, even though there's a good heuristic evidence that they do so. It's a highly challenging and difficult question. Machine learning is changing the world we live in. It's ubiquitous. ChatGPT is everywhere. There's a new rolling out of a new ChatGPT X for large X. Any speech recognition is based on that. And given that machine learning is so important in technological developments and that quantum algorithms can solve some highly structured problems efficiently that classical computers can't, it makes a lot of sense to ask, is there a scope in quantum machine learning? And that's also a question we looked at a lot in recent years. Again, in a somewhat manic depressive fashion. To start with, yes, we can. I was tempted to say there are separations in that quantum computers can solve some well-defined learning problems in the sense of Puck learning. There's a bit of epsilon and delta here. In the generator and distribution learning sense, that is super polynomially faster than classical computers, where you take samples and you want to learn a generator that spits out new, say, pictures of cats and dogs, and there's a proven separation in that quantum computers can learn super polynomially better than classical computers. The field exists. Whoa, that's very inspiring. At the same time, the data are not very plausible. They are highly constructed as a proof, it's not so easy, but they are not natural. They're not handwritten numbers, no pictures of cats and dogs. If you want pictures of cats and dogs, you can also do something. We've understood that there is quantum algorithms that train not quantum networks, but classical networks, large-scale pruned, sparse classical networks, and we could show that there's training algorithms that have a proven separation over large classes of classical training algorithms. Which is kind of cool. You do quantum mechanics, but in the training of a classical large-scale network. And that works also for realistic data. Yeah, for industrially relevant data, we tested this on the C400 data set, or we have benchmarked with a model with 7 up to 103 million parameters, which works well. So that does work for numbers, for pictures of cats and dogs. That cat is not from the data set. It's actually our cat, Minchen. I made it a habit to get up every morning at 4. I take my cup of coffee, I open my laptop, and then Minchen also gets awake, sits on the laptop, looks very smart, and also takes his paw and dips into the coffee, but doesn't like it. But the cat thinks that's how we do it in our household. You're also busy as an academic. But you see, quantum computers can help in training natural data, pictures of cats and dogs. These are still very deep circuits. You can ask, are there short circuits that do something? Yes, we can also do that. That's in the making. There's constant depth quantum circuits that have a proven separation to log depth classical circuits with meaningful mathematical fine print. That's totally reasonable for natural experimental stuff you can do today, but again, the data are somewhat academic. You see what the manic depressive part here is. There's the cool thing in the middle, industrial relevant applications, and we come from all sides and come closer to it, make good method development, but the big thing is still somewhat elusive. But it's still extremely motivating to think about these problems. But there's also depressive phases. We found, and also others, that noise is pretty harmful. If you don't do anything about this, you're basically sinking into the ground of noise, and all you have is logarithmically deep circuits in a precise sense. Ask me about this under general noise models. You can do so-called error mitigation, which is you take data and you learn what's going on, you undo some of the noise. It's in the center of the IBM strategy. But we found that there's an information theoretic obstruction already at log deep circuits. There's the mathematician's joke that log is upper bounded by 4. It's a good joke if you think about this. It's basically constant. I'm not saying we got lots of phone calls from IBM Zurich that day. Yes, but very respectful ones. I'm not saying error mitigation doesn't work. It's a great method. It should be done, but it's just not scalable in the most drastic of all fashions. Yeah? Eat it. A bit of a depression. That said, you can do quantum error correction. You can correct for errors in quantum computers. You measure and you do something. You say, wait, are you honest? This guy said you cannot measure without changing the state. And that's right. But there's so clever measurements that let you learn about the error that has happened, but you learn exactly nothing about the logical information that's being encoded. Because if you did, you would change the state. That's the idea of quantum error correction. And that's something that was seen like 10 years ahead. And then just before Christmas, this guy in the middle is my former student, just before Christmas, a team of people set out to build a 256 physical qubit, 56 logical qubit, error-corrected device, had error-encoded circuits running, where everybody thought, how is this possible? That's like 5 years too early. That also happens that there's a lot of activity now also by other players on quantum error correction that's way faster than we thought, giving rise to a manic phase in a certain sense. maybe the most plausible application, that's already my last point I'm making, for the next years is in simulation. And you might say that's a fringe area. By no means. Take Lufthansa. They're training new pilots, not on new Air 380. It would be expensive, but on the simulator in Hamburg. Quantum materials are being simulated on large-scale computers with like 1 million CPU hours per day. It's about a third of the computing power of modern supercomputers that is run on quantum materials and quantum chemistry. It's amazing. Climate is also a big chunk, but a third is for materials. And then you say, can quantum systems simulate quantum systems? Like 10 years ago, with friends here in Munich that we collaborate still a lot with, we made a simulation of that type that was quite stimulating at the time. You start out with atom, nothing, atom, nothing, atom, nothing, and then you let it go in a quantum simulator under precisely controlled conditions. And Emmanuel did this. But we not fitted the data, but we made a classical resimulation of on the fastest computer available at that time, the Jülich Supercomputing Center, on a still pretty large economy, Germany, and with 5 weeks of runtime per plot, which is the upper limit if you have a PhD student involved, unless they comply, that gives a plot of this kind. It's like the upper limit you can do. It works for short times, but boom, there's a barrier you cannot overcome in time, because the state gets too entangled so that you cannot faithfully represent it anymore. But the quantum simulation runs on. You can ask questions about the physics better based on the quantum simulator than on the classical resimulation. It's a baby step, or it's 10 years ago, but it was a baby step, a healthy baby step in a pretty good direction. And this is an idea that carries much further. It's a new way of thinking about physics. You don't think of new theories, but you probe nature under precisely controlled conditions in the lab. So you can ask, what does mean by delocalization? You go into the lab and find out. What's the foundations of statistical physics? You go into the lab and find out. My parental advice today is, don't do experiments with real black holes. It's going to be nasty. But you can do this in the lab. You can do space-time experiments in the lab, and we are doing this with our friends in Munich, Vienna, and other places where you ask nature what it is about under extremely precisely controlled special-purpose quantum computers. So quantum simulators can beat the best supercomputers we have available today, but it remains a race of quantum over classical. Which brings me to the end. I said I would not run over time, so let's meditate on what we have seen in our journey today. So, quantum computers are no longer fiction. They develop extremely rapidly, like in an explosion of activities. Yes, yes, yes. But now serious method development is needed on hardware, but also on software. We have to find out what can we do with these new devices. And that's a truly interdisciplinary endeavor between theoretical physics, experimental physics, mathematics, machine learning, computer science. Everybody talks about this, but we live this. These things must come together if you want to make progress. And even the good old questions of, say, the foundations of physics come in. And where can you work on the foundations of physics and go all the way the food chain to the technological application? That's an inspiring field to be in. Quantum computers will disrupt supercomputing. There's little doubt about this. They have applications in simulation, material science, machine learning, optimization, and others. There's evidence to the effect of all of these applications. That's exciting, that's stimulating. So many people are taking this quite seriously. For example, one paper by IBM had 500 people on the contributor list. Think about this, like a tech person in the US makes like at least 200,000 a year or something. 200,000 times 500, it's easy to calculate. For a private company, they're not getting government funds. It's pretty impressive. But there's also large government funds. For example, the European Union funds this in the quantum flagship with $1 billion. The German government does so with 2 ministries. The reason why this talk had to be shifted is because I have to consult them later in the afternoon, so I will be out for an hour. But they've made a big program on this, and they invested $2 billion. which is quite impressive for a relatively small country like Germany. They have this in the center of their strategy. It's a wonderful program that pushes Germany ahead quite a bit. There's the program by Bavaria, the so-called Munich Quantum Valley. That's Bavaria and us in Berlin. I'm very happy that the biggest funders is the Bavarian taxpayer. Thanks so very much indeed. But there's also a Berlin program that we set up, the Berlin Quantum Program. Somebody's, I think, listening in from Berlin. That's also a wonderful local program that we are setting up in Berlin. Quantum computing is exciting. It's going through the roof. There's many developments. It's hardware challenging. There's interesting technology coming in, interesting experiments coming in, but it's also theoretically stimulating. You have to think, what can we do with ideas of computer science, mathematics, and physics? The roof is the limit in a way, but at the same time, I also often say is that we have to be realistic, we have to be based, and in a field where so much money flows in and so interesting applications are plausible, there's also gigantic expectations, maybe sometimes too big expectations. There's also a bit of an element of hype involved, where people say, we beschleunigen alle Prozesse. We don't beschleunigen alle Prozesse. Yeah? So we have to be realistic, but that doesn't mean it's not exciting. So I end this talk on the note that I think that quantum computing is exciting, even if one resorts to saying things that are true. And on that note, I thank you very much for your attention. I'm looking forward to questions you might possibly have. Thank you very much.
Yeah, thanks a lot, Jens Eisert. Perfect for your wonderful and insightful talk about the basics of quantum computing, but also showing us what they're able to do, what issues we have, also showing some research topics, how you overcome these issues. Do we have questions here in the audience? There's one.
Yeah. Thank you for the interesting and engaging talk. You mentioned prime factorization and how it applies to the asymmetric encryption that we use. That's right. So my question would be, how many stable qubits do you need to break state-of-the-art encryption by doing fast prime factorization? And how far away from that are we on an optimistic timescale?
Yeah, that's a very good question. I try to answer as honestly as I can. So Shor's algorithm is presumably the most interesting application in some way, but it's also the furthest away. It's like really a high bar, I would say. So people don't expect Shor to provide any meaningful answers without quantum error correction, because it's so complicated that you have to run a fault-tolerant quantum computer that comes along with many overheads in physical qubits compared to the logical ones. There's good expectations for that. It will be easily in the millions. Yeah, so it will be in the millions before you can come close to meaningful applications of that type if you include the physical qubits. And you should also be aware of the fact that the quantum device is big, but you will have to have a classical supercomputer next door that operates on things, controls things, but also error correction has to be run on the scale where the actual errors are happening. And that has to be quick. You have to run like stellar automata or something to decode the problem. So there will be a quantum computer, there will be a big supercomputer and a power station next door that runs the thing. Yeah.
So we'll see it coming, basically.
Yeah, that's right. So this looks like very far away in the future. It's very difficult to assess, honestly, because I mean, a couple of million seems far away. Yes, but the issue is size doesn't matter so much. It's not so difficult to make large-scale computers. Even millions is not completely implausible. To make them well is the problem. To get good average gate fidelities is challenging, and that's super challenging. I mean, no doubt about this. But then, I mean, who would have thought that we have like over 1,000 qubit quantum computers now? I mean, 5 years ago, people would have thought, please. I mean, Schrödinger was thinking a single atom was inconceivable for them. Yeah, I mean, let's see.
Just because for time reasons, do we have a question online? No, then I continue here.
Thank you. Hi, I've read that biology. In biology, there's quantum computing or quantum processes going on, photosynthesis, for example, and some people even speculate the human brain or consciousness might be somehow quantum. related, can you comment on what we can learn from biology, and is that applicable to quantum computing going forward?
That's another wonderful question. Thanks so very much indeed. Yes, that's a field called quantum biology. And I mean, there's evidence in a couple of processes, I think 3 to my knowledge, where it's pretty clear that quantum mechanics, quantum effects matter in a reasonable way. I could spend like half an hour of defining what that means, but say photosynthesis, you mentioned this yourself, cannot be explained without coherent dynamics being truly quantum. There is a kind of a compass in birds that's also quantum. There's like 3 famous examples which are really evidently quantum, and there's no way you could explain them without quantum. So that's great. Nature uses quantum mechanics. That's the good news, the manic phase. The depressive phase is that it seems to be hard to find other good examples of that type. There's these 3 examples, and things are a bit stuck there. Yeah, so it's not. Nature doesn't seem to ubiquitously use quantum effects. It's a bit of a rare thing. And the brain, I've actually written a review article early on the potential of the quantum, the brain being a quantum computer. While I tend to be a rather optimistic person, I hope this came across, I'm not very optimistic here in that I do think that the brain is a classical computer. It's a kind of a Turing machine, if you want. And well, there's an article by Penrose about this. You must know this, or a book. I don't think that large-scale coherence would necessarily matter in the brain, but who knows? I mean, part of the charm in the field is that foundational questions are so close to technological questions. I just published a paper on where temperature comes from. And we made good progress, hard method development, where temperature comes from. Don't get me going. And then the next day you publish on error mitigation in quantum computing. Yeah.
Just info, in addition, we don't have too much time left, so 1 or 2 questions, and then I would ask you to find Jens Eisert later here in the motor world and ask them.
You're between lunch and
yeah.
yeah.
I would like to expand on the first question. So some of the problems you mentioned, like the cats and dogs and the Porsche cars, they involve lots of data, gigabytes. Typically, the matrix A in your thing is big. Do you have to store this data in quantum memory, or is there a way around doing that?
Oh, that's a long question. I keep it short. Okay, I read the meta text, and the meta, to explain me, he's an expert, also in Munich, a well-known figure. So the upshot is that yes, you have to get the classical data, and that's a huge topic, and this is also subtle, because there's some encodings, for example, things called QRAMs and so on, that are very powerful, but people think they're kind of too powerful. So one has to be careful that one doesn't sneak in unrealistic power in the way you get classical data into the quantum computer. So no matter what you do, you have to get the classical data into the quantum computer. Yes, I mean, that's right. But you should do so in a way that's easy and efficient. For example, in the CATS paper I mentioned that we did with 3 friends, they're all called Liu. They're not related, from Chicago, and they're all more hyper than I am, which is already something. And in this paper, we had, it's 5 pages, blah, blah, nature, communications, but then we have a 70 pages mathematical paper with lemma theorem. And in this lemma theorem, we very carefully checked the circuit complexity of the encoding. We don't use QRAM, it's sparse enough, so the uploading is important. So when the meta text of your question is, dudes, be careful about the encoding, you could possibly sneak in unrealistic resources, then I agree. And every serious paper has to be equipped with a parental advice on how you encode. Hello.
I have seen one last question, or maybe there were more questions in the room, but one we can answer in time.
Hello, one question from me. So IBM is currently building the largest quantum computers that we have available in the cloud. And what they're doing is building sort of very sparsely connected quantum computers with gates only able to access a few qubits and sort of scaling it very much horizontally. And I was wondering if that's sort of that's what they're doing because they can do it, or if this is actually sort of leading us to a place where we can solve very large problems or if this sparsely connection will actually impose an actual limit to what we can do.
Good. I have a lot to say about this, but I will not because there's lunch coming up, and also there might be IP property rights of IBM, and we're too close to them. But I think what I'm saying now, I can say, which is yes. The known structures are like a layer-wise, they're very sparsely connected, as you say. The design principle was done because you wanted to have it in 2D on superconducting chips, and they wanted to avoid crosstalk. So they did it in a way so that the average gate fidelity are optimized, roughly. And this is super nice, and it works super well, and that was the underpinning of the architecture. They realized the same as you seemingly did, in that, yeah, that's great, but it's not so great for some applications. Like some methods of quantum error correction also don't work so well for that kind of connection. You want more connections, like LDPC codes or something. They want long-range connections. Yeah? So they noticed this, and the chips in the development will be more connected for the reasons you mentioned. But I think that's all I can say, unless, I don't know.
Then thanks again for answering all of your questions. Yes.